Hello everyone and welcome to my presentation. Today I'm going to discuss my research over electrocatalytic carbon dioxide reduction, which I work on under Dr. Massey. So first and foremost, let's go over why we are aiming to reduce CO2. So global warming is changing our climate in a major way. The average temperature is rising at a faster rate than ever before seen. Greenhouse gases, such as CO2, are causing this change, and we are to blame for the rise of CO2 levels in our atmosphere. The combustion of fossil fuels in our vehicles and factories leads to this rise. Although there are different reactions to reduce CO2, we are aiming at reducing it into CO. So here is the reaction, and here is the free energy and the cell potential of the reaction. Now, this reaction is not spontaneous, meaning we need to put in energy for the reaction to go. However, by adding a catalyst, we are able to lower the activation energy for the reaction and increase the reaction rate. Now let's look at how the electrochemical reduction of CO2 to CO will benefit our atmosphere and us. As I mentioned before, this reaction is not favorable, so in order to go, we need to input energy such as solar or wind energy. Now, this will be the electricity to power the reaction to go. However, a catalyst will also be included to drive the reaction forward at an increased rate. Once CO2 has been reduced to CO, the CO will be a precursor that will be changed into a fuel source. So why the fuel source? Going back to the fossil fuels which we so heavily rely on, these are not going to last forever, and we need to look at creating alternative fuel sources as well, as at the effects the after products will cause. So here, this fuel source will go over to our vehicles, factories, machinery, etc. to be used up and combusted back down to CO2. The cool thing about the CO2 that we will create, will be collected and go right back to being reduced and again create a fuel source. Now this is a cycle we create will help to stop the increase of CO2 in our atmosphere. So this cycle has many different but important parts to it, but here in Dr. Massey's research lab, we are focusing on at the reduction step and creating an effective and efficient catalyst. There are actually many different catalysts that can be used for this electrochemical reduction. We chose to synthesize and explore the efficiency of N-heterocyclic catalyst with a manganese center, specifically manganese N-heterocyclic tricarbonyl halide catalyst. Now, here we see our manganese methylbenzene tricarbonyl bromide catalyst, which we are currently synthesizing in our lab. This catalyst has been tested and explored for its effectiveness and efficiency at reducing CO2 to CO. However, it's been determined to not be efficient as the amount of energy required is still too high. Here we see a similar catalyst. It's our manganese methylbenzene tricarbonyl bromide catalyst. Although the methylbenzene has been synthesized and used for different catalysts and compounds, this catalyst has yet to have any published data for its effectiveness and efficiency. These two catalysts are quite similar, except for the extra carbon present in the latter that changes the bite angle to which the ligand is coordinated onto the metal center. We hypothesize that this change in bite angle will increase the efficiency of the catalyst. One of the reasons why the former catalyst is inefficient is the amount of time it takes to synthesize it, since we make the ligand and then coordinate it onto the manganese. In our lab, we first aim to reduce the time it takes to synthesize the former catalyst by modifying its procedure, apply it to the latter catalyst, and then test both catalysts and compare them to determine whether the bite angle and procedure change was enough to consider it an efficient catalyst. Here I have the general goals of our research lab. First, we want to have a modified and set procedure for the synthesis of the methylbenzene ligand. Then, we will use this procedure to synthesize the methylbenzene ligand. Next, we will coordinate the ligands onto the metal, but depending on how many research students Dr. Massey has, coordinating the methylbenzene onto the manganese could coincide with making the methylbenzene ligand. And then finally, to test the two catalysts on their ability to reduce CO2 to CO. Now, one of the major players to speed up the synthesis time of the catalyst is to use a microwave for the reaction to go. Within the microwave, we are able to stir the reaction, set the temperature, and modify the pressure for which our reactions will proceed under. This is meant to reduce the time needed for reactions. In our case, we used the microwave to synthesize our precursor ligand, benzene, to cut down on the time it takes based on the literature. It actually takes more than 11 hours under reflux for the reaction to go. Since the conditions in a microwave reaction can vary, here in the table we have listed the different solvents we've tried, as well as the time and temperature. Reaction A was my very first reaction, and it just so happened to be the first reaction we performed in the microwave, and we're lucky enough to get a decent yield for our first, as it was our first reaction. For reaction B and C, product was confirmed as well, but only reaction A and B had enough to continue on to the next step. Reaction C was very time consuming as it was very hard to remove the DMSO, and reaction D was inconclusive. Now let's go into the synthesis of the ligand. Here we have benzimidazole reacting with 2-bromopyridine in the microwave under these conditions. To make the precursor ligand we refer to as benzene. Here we have our microwave, so we get a microwave reaction tube, add the solids, add the stir bar, add the 2-bromopyridine in the hood, then close it with a cap. And then purge it for 5 minutes, meaning we hook it up to the nitrogen gas line so that it pushes out all the air and is under an inert atmosphere. Next, the tube was placed in the microwave, so like right there. And then the reaction proceeded based on the settings set up by the computer. Once the reaction completed, we used TLC to confirm the product was made, then looked at NMR to see what was there. And once satisfied with what we saw, flash chromatography was used to purify the benzene, and again, NMR was used to confirm the product. And once to what we expected. Now, right off the bat, we are able to assign the tall singlet as this hydrogen, or hydrogen attached to that carbon. And all the other peaks resulted from the rings present in the benzene, caused these multiplets to appear. Finally, comparing the NMR spectra to published literature, we were content that we had made benzene. Next comes the methylation step, which seemed to give me a little bit more trouble than I expected. So we tried cutting down on the time needed for the methylation by having the reaction go in the presence of KOH and DMF. Since all we were trying to do was add a methyl onto this nitrogen. And idomethane is very harmful, so this caused us to take precautions when handling it. Here in the image, we see the Schlenk flask hooked up to the nitrogen line. So right here is where it's hooked up to the line. This is the Schlenk flask, and it's sitting in an ice bath for the reaction to go. And there's like a little stir bar in there. So a major issue I had with this was removing the DMF. So we thought about using a roadmap, but agreed that it was best to not let the idomethane to be out in the open or exposed into the roadmap. So instead, we just kind of, once the reaction was over, we tried confirming it with TLC plate. However, it came out kind of odd, but it was clear that something was there. So we moved on to the purification, which was removing the DMF. After trying different ways of extraction, even using an azeotrope, I finally just decided to wash and extract it with water and brine. However, it took a bit of time. So once it actually seemed pure, like after washing it a couple of times, and yeah, I ran NMR on it, but it was very different from the BIMPI NMR, which I kind of only expected there to be an extra methyl peak and maybe like a slight shift, but it seemed like there were more things present. It seemed like some of the shifts that were I figured should have been there were not there anymore. So it just didn't seem like it was actually methylbenzene. After struggling quite a bit, I decided to go back to the literature and come up with a reaction following their reflux reaction, which is what you see here, and these are the conditions of my reflux reaction. So here we see the Schlenk flask, which is this buddy right here. I added the BIMPI and then the stir bar, and then purged or closed it off with the septa, which is this one, and then I went ahead and added the condenser, and then closed it off with the septa as well, and the vent needle. And then here is the tubing to the nitrogen. So I purged it for 5 minutes, and afterwards I added the acetonitrile through a needle or syringe through this septa, and then same thing with the iodomethane. And then I lowered the flask into the oil bath, and left it on there for 11 hours at 80 degrees Celsius, and also turned on the water for the condenser here. So once it was over, the product was collected. So we put this in on the Rotovap and let the acetonitrile leave, and then I redissolved it in acetylnitrile and then crashed it out with diethyl ether, and then we filtered it out. So once it was dry, I ran NMR on it, and it was still messy and kind of like noisy. So it seemed like it had impurities in it. So I redissolved it and then crashed it out again, and then finally got an acceptable or clean NMR, and I was able to conclude that methylbenzene was made. I didn't actually include the NMR here because I ended up getting the NMR after turning in the presentation or this PowerPoint, and then I actually got the NMR right before classes were switched online. I have a paper copy, and I was thinking about including it on here last minute just to show you guys, but the paper copy, there was not a good way for me to scan it without taking a picture of it on my phone, and it just did not seem presentation worthy, so I just went ahead and left it out. But yeah, I was able to confirm that methylbenzene was there based on the peaks I saw. Now that we have the ligand synthesized, do we go straight to coordinating it onto the metal? No, we don't. So this reaction here is called metathesis, and it's just switching the iodide ion for the PF6 ion. And so the iodide ion is a halide, and it's the same as for the bromide on the manganese. Because they're both halides, switching out for them is actually pretty or easier and could possibly happen, which is something that we don't want, because just having the iodide on it turns it into a different catalyst. So switching out the iodide for the PF6 is the best. It's like the next step for us. And so plus PF6 is actually too weak to switch out with the bromide, or it doesn't want to switch out with the bromide. So now that we have the correct counter ion, we can coordinate the ligand onto the manganese pentacarbonyl bromide, and to get the manganese methylbenzene tricarbonyl bromide. So now that we have our procedure for getting the catalyst, the manganese methylben-P tricarbonyl catalyst, we can use that same procedure for getting the manganese methylben-PIC tricarbonyl bromide catalyst. And so here we have our benzimidazole. Here is the pyridine again. It just has the extra carbon right here. So we attach them together to get our methylben-PIC, or our ben-PIC, I'm sorry. And then we do the methylation step, which is right here, to get our methylben-PIC with the ion. So then again, we go through metathesis and switch out the iodide ion for the PS6. Now that we have the correct counter ion on there, we can coordinate it onto the manganese pentacarbonyl bromide and get our manganese methylben-PIC bromide tricarbonyl bromide catalyst. So as I said, there are other catalysts for CO2 reduction. This is actually complexes that are undergoing 1 electron and 2 electron reactions. And I included this because these actually show the cell potential and the free energy. It's actually the cell potential that we care about because that's what we are going to look at when we compare how effective our catalysts are, how we compare them to each other, and then overall how effective each one is, looking at how much energy we put into making the catalyst, and then how much energy it is to reduce the carbon dioxide to CO. So I would like to say thank you to Dr. Massey for letting me be a part of her research group, for Alexa Ramick because she's the one who convinced Massey to, right here, to start doing research. Alec Filson, he is actually working on the microwave aspect of our stuff, so he's trying to figure out the best conditions that work in the microwave for our reaction. Nick, he is no longer a part of our research group, but he actually won an award for presenting our research at UAMS. And then Layman and Andrew, they're over here. They are new to our research group, and they're, getting trained up and about to be part of something amazing. So hope they have fun. And then our funding, of course, University of Central Arkansas University Research Council. So thank you, and I hope you guys enjoyed my presentation and my research.